Capacitors are everywhere around us. You can see them sticking out of your desktop motherboard, and you can also see them in big news articles, such as the recent one about Tesla's new power system, which involves a battery and a capacitor. Now you might be wondering, what are capacitors? In this video, we will discuss how they work, we will make our own capacitor, and show one in action. Right, so let's discuss the concept of capacitors based on a standard circuit. So this circuit is just a power supply with a wire looping around from the positive terminal to the negative terminal. Now inside a circuit, the electrons travel from the negative terminal to the positive terminal this way. And from the positive terminal, a positive molecule called the holes travel this way. Now the difference between the negative and the positive creates something called a potential difference. And this potential difference causes the current to flow, which therefore causes electric energy. The thing is, in this circuit, when the power supply shuts down, the potential difference is gone, and therefore the circuit shuts down. There is no more current flowing, therefore no more potential difference, therefore no power. Now this is what a circuit looks like with a capacitor. So similar to before, the negative charges with the electrons flow through this way, and the positive charge with the holes flow this way. One different thing is that the negative charges flow into the capacitor this way, but it cannot cross because the middle is blocked by an insulator, just like so. In that case, similarly, the positive charge cannot go through the capacitor as well, so a positive charge is locked here. Of course, because these are linked in parallel, the charges can fully circle around the circuit area where the light bulb is located. Now what happens inside the capacitor is that because they cannot pass through, a negative charge builds up here. And because the positive charge cannot pass through there as well, a positive charge is created over here as well. Now, I mentioned that the difference between the positive and the negative charge creates something called a potential difference, which drives a current. Now, a capacitor, by storing this difference in charges in two conductive plates, has managed to create that exact potential difference. Now, what happens when I turn off the power supply, just like so, is that the negative charges and the positive charges want to neutralize themselves, so they will leave. What happens is, for a short time, the electrons flow from the capacitor to the lamp, and the positive charge also flows from the capacitor to the lamp. Therefore, as you can see, a current has been established. Now, a capacitor is able to discharge and charge very quickly, because the method of storing electrical power is not in the form of a chemical reaction, but because they store raw potential difference between their plates. Due to this, a short charge such as a mere second can charge up the capacitor to full capacity. And by connecting the circuit with the capacitor is able to discharge its charges very quickly. This makes it very useful in the industrial sense, as mentioned before in the article about Tesla cars. Now let's move on to my design of a capacitor and how I will use it in my experiment. Before I start, I want to talk about how my capacitor is going to look like and what it's made out of. So as I said before, a capacitor is composed of conductive material and insulating material. So what I chose was, for the conductive material, I chose to use aluminum foil because it is the most available conductive material that I can use right now. For the insulator, I decided to go with paper because paper is common in my household and it serves as a pretty good insulator as well. So two sheets of aluminum act as the positive and the negative terminals. Afterwards, paper will be placed in between them and outside them so that it is shielded from the outside and with each other. When a capacitor is exposed to the surrounding, especially the conductive parts, it starts to lose voltage because, as I said before, they want to remain neutral, so it starts losing voltage to anything it touches. It could be your body, it could be the air, it could be each other, and it will be a big problem. So in order to ensure that the leakage of voltage is set to minimum, I will have to wrap them around my paper and attach them, then roll it up to create a cylinder which will provide the most insulated figure that I can make at this current point in time. Right, so this is what a finished capacitor looks like. It's basically 2 sheets of aluminum foil separated by sheets of paper and wrapped around so it has a nice cylindrical shape. Now you can see here the wires are connected to each aluminum foil section so that it can act as the positive and negative terminal in the experiment to come. Usually calculating the capacitance of these kinds of capacitors is quite confusing since you need to take account into the distance, the properties of paper, aluminum foil, etc. But thankfully, I do have a multimeter, and this has the option of measuring the capacitance. So as you can see in the voltmeter right now, or the multimeter, it's currently reading 1.205 nanofarads, and this is because the pins themselves have a very small capacitance. Now, nanofarads is quite low, but let's hook this up to the capacitor and see what it reads. I doubt this is going to be efficient, but hook it up. And there we go. Now it's reading 6.68 nanofarad. So subtracting 6.68 by approximately 1.5 gives us about 5.1 nanofarads of capacitance, rounded to the 2 significant figures. Right. Yeah, that's not impressive. To put this number into context, a conventional capacitor has about 0.1 to 1 microfarads of capacitance. Now 1 microfarad is 1 nanofarad times 1,000, so if we reference it to the weakest possible conventional capacitor and compare it to ours, we get the number that is about 20 times as powerful, and the highest is around 200 times powerful than our mini capacitor. Seeing how inefficient our capacitor is, I doubt it will be able to do anything amazing like lighting up a light bulb with its stored voltage, but I'm sure we'll be able to see how it functions using a voltmeter. So off to the circuit we go. So this is my experimental circuit to test out the capacitor. So as you can see, the wires connect from the PSU to the capacitor and the multimeter, which is currently set to volts, in parallel, so that the current flowing through from the power supply will be able to charge the capacitor, but also send power to the voltmeter to see the difference regarding the effect of the capacitor. Now there's a switch over here which is currently preventing the power supply from supplying power to the capacitor and through the voltmeter. And the reason why the voltmeter is currently reading 0.53 millivolts is because some potential difference does exist between just by the existence of this 2 prongs connected to a metal piece. So that will not be a big problem, as the resulting capacitor's discharge will be much greater than 0.54 millivolts. Right, so I'll give this about 15 seconds of charging time, and let's see how it goes. Right, 15 seconds is up, turning it off. Okay, stabilizing. Right. So based on the current readings, we can assume that this capacitor has the ability to contain about 320 to 340 millivolts, which is 0.320 to 340 volts. Now you might be wondering, if the capacitor can hold around 300 millivolts of voltage, then why did it still drop? Well, this has to do with the leakage mentioned before. A commercial capacitor is wrapped around with insulating materials in order to prevent the conductive parts from being exposed to the environment. As you can see in this diagram, the aluminum foil, or the cathode and the anodes, the positive and negative terminals of this capacitor, is wrapped around with a dense layer of a insulating separator. Also, the outside is covered with an insulating sleeve, which is either made out of plastic or sometimes rubberish material in order to prevent the outer layer of the aluminum from being exposed to the environment. Now this is where my capacitor shows its inefficiency. Number 1, the paper is not as tightly wrapped around as the insulating sleeve of a commercial capacitor would be. This causes some areas where voltage can leak through. Secondly, if you take a closer look at the edge of the capacitor, you can see that the edge is not fully insulated. Usually the edge is covered up with the insulating sleeve to prevent air or outside environment from touching the capacitors. However, because of my capacitor being made out of A4 paper and aluminum, I was not able to fully insulate the edges of the capacitor. This made another big area where voltage can leak. With that, this video comes to an end. I hope you found this informative, and hopefully I helped you learn something new today. Thank you for listening, and I'll see you next time.